Diogo, should we start now? As I see people joining.
Yes, sure.
Okay.
We are on time.
Okay, so 1 minute late, it's time to start the second day of CIoT 2020. And so good morning, good afternoon to all of you. So today as the keynote number 2, we are pleased to welcome Professor Hervé Rivano, who is a professor at INSA Lyon. And Hervé, in a few words, is the head of a very strong team dedicated to smart cities. They are doing a lot of nice stuff. And so I hopefully today and also tomorrow's keynote by Rafael Bruno will be very complimentary. And I'm sure you all enjoy these talks and learn a lot from these guys who have been developing a lot on these areas. So today, Hervé decided to talk about one of the topics he works on, which will be on air quality using wireless sensor networks. So with a few names on the slides, you can see. So Hervé, the floor is yours. I remind you that you have participants through WebEx and also on YouTube. So if any people on YouTube wish to make questions, don't hesitate, and I will relay the questions to Hervé. So Hervé, the floor is yours, and you can start whenever you want.
Okay, thank you, Marcelo. Hi, everybody. It's a great pleasure to be in my place talking to you. I'm very honored to have been asked to do this keynote. And so I will talk to you about problems that we are looking for the last, let's say, 6 years on trying to monitor and to work with air quality, outdoor air quality mostly, with low-cost devices, in particular with wireless sensor networks. And you will see that it's a little bit more complicated than the work that has been done on wireless sensor network for the last 2 or 3 decades. When you go to practical phenomenon to monitor, but of course, what we did take roots on the work of all the community on wireless sensor network. So you see a lot of names on the slide, but since we're French, I have to give credits to thousands of labs, people giving money or data or whatever. But I would mostly want to highlight that this work is so it's a long strike of research done with one of my colleagues in my team, Walid Beshkit, who is assistant professor, and Bérangère Lebentel, who is a researcher at IFSTAR. And we worked with several PhD students. Sorry. So the first one was Ahmed Boubrima. He defended his thesis last year, and now he's working as a postdoc at Rice University, and they are doing very, very nice things at that place. And there are still three PhD theses working right now on this topic. One will defend in two months. And we had the chance to have the support of an engineer, Manuel down. You will see that what we did on the practical things. So I won't go into all the details of who gave him what on which part of the project. It's not interesting, but it's to say the work belongs to all this very talented young researcher with me. So let's go into the thing. I'm pretty sure that many of you are aware of the fact that air pollution is one of the big challenge that the cities of today face. And sometimes the figures are really striking. Like it's killing people. a lot of people every year. It's costing a lot of money. So to be very cynical, it's a topic where you could suppose that even states of the cities are ready to put money on it because there is a lot of money to do with that. But the real problem is a problem of sanitary problem. And so we are not contributing to reducing the problem, but to understand and know the problem so that the political decisions that are needed, in particular in the smart cities projects, can be done to target the real source of pollution. You have to monitor it conveniently. The thing is that, okay, air quality is monitored for a long time. And today, the state of the art is a mix of models, in particular physicochemical models that come from fluid theory, chemics, that try to put in equation how the pollution is spreading within a city. But for your model to run, you need to have inputs. So you need to know where are the sources of pollution, how they emit pollution, what is the meteorological conditions, and stuff like this. So you need to have some sensors. And most of these inputs, in particular the inputs of the sources of pollution, are very approximated. That's one of the big problem is that the traffic is not known precisely. The emission by the cars or the trucks is not known precisely, so it's statistical. So the models compute the pollution from statistics on the emissions. And then you have some monitoring station that are reference stations with very accurate, very efficient, but very high cost also. Also like the one that you have in these two pictures. And these monitoring stations, they are there not to to give input to the model, but to correct the model and to calibrate the model once he has done its computation. The thing is that this kind of stations are very expensive and very big. You need to have power. You need to have so you don't care about the network because you will have 4G or ADSL connection, and you have some sensors that are very, very expensive. The one on the right side here is an example of something that costs tens of thousands of euros, but you have some that are even more expensive. So you don't have a lot of stations. For example, around Paris, around the capital of France, you have some tens of stations that allows to recalibrate the models, but it's not very dense. And the thing is, we are having on the market better and better low-cost sensors that start to be a thing, that they start to be interesting to do real measurements. And so that's why we're trying to work with. So the idea of this low-cost sensor, you have one example on the right side. You see the size of it. This one is not one of the smallest one, but it's one that is really used in practice in several microsensors to monitor nitro deoxygen, NO2. I don't know. I'm not very good at chemics, so in English it's even worse. But you see the size of it. The previous one I show you was something that taking the size of 3U of like a very big network switch, like a big one. So we have these sensors that are small. They are cheap compared to the big ones. So we can envision to have a lot of them deployed to have a good spatio-temporal granularity of measurement. But then we have all the problems that comes with the density of deployments, is that we need to have autonomy, we need to have self-organization, we need to have good deployments. And the other counterpart is that, okay, they're cheaper, so they are less accurate to the lab grade ones. And they have a question of lifetime that I will try to address at the end of the talk. So it's not a question of autonomy in terms of energy, it's a question of lifetime, the time where they can give good values before to degrade themselves. And so what we will have is we have a phenomenon, we have sensors, we have a wireless network on it because they are too dense or maybe mobile to be wired, and then that data collection and processing. And so that's the outline of the work that we did since the last 5-6 years with several projects, but we don't care about that. And I will try to show you some parts of the contribution that we had. I will not go into all the details, of course, because of time. I will not talk a lot about the I will not talk about the sociological study, but if you have question on that, be pleased to ask. But the thing is that all of this is necessary pluridisciplinary. You need to work with people that are not only computer scientists, not only people from the measurement, but also people from the models, people from the urbanism, people that understand all the dimensions of the problem. But let's start easy. So we have a deployment problem. And if we take a part of a city, so that's a map of pollution around the main train station in Lyon. And we have some kind of potential position to deploy the sensor. So in this example, the positions are on a regular grid. For it's a TIE example, it should be more correlated to the streets, but it's not the purpose there. And let just have a look at the combinatorial problem that we have here, that if we want to deploy 12 sensors among the 225 positions that are on this grid, then you have 10 to the 19 possibilities. And if you increase a little bit the number of sensors, it grows exponentially. So, okay, it's not a problem that you can solve by hand. You cannot solve it by looking at the problem and say, okay, this part is interesting. It's too complex. It's too combinatorial. So you need to have some optimization problems. So hopefully it's my field at the beginning. So I had fun on that. You will see some equations. So we have to compute the best deployment, but we have also to make sure that the network is connected, and we have to take into account all the problems of sensing errors, heterogeneity of nodes eventually, and all the problems that comes from the practical situation that we are looking at. So if we look at a generic methodology, the thing is we can start and try to identify the sources of pollution and their emission. So that's something that is only if you look at pollutions, industrial pollutions, for example, that comes from very specific points, and you want to monitor if there are some thresholds that are crossed and there is a sanitary problem, for example, or a chemical accident somewhere that you need to warn the population, for example. So once you have the source of pollutions and you know the emission, so that's big hypothesis, then you have to take into account the dispersion model in the atmosphere. So how the pollution will spread in your space. And then you have to monitor that with sensors, and your sensors are not perfect. They make some errors because they are low-cost sensors. So you need to take also into account the fact that they have these errors, and you have an error model. So you put all of this, and then you have an optimization problem is how to optimize the deployment of the network with budget constraints or coverage constraints. You want to to ensure the fact that you will detect a threshold crossing if it happens, and that your network is connected. So that's the drawing at the bottom. You have some emissions made by the sources with all the colors, and you say, okay, if I put a sensor there, maybe I will be able to detect the threshold crossing from source zone 1 or zone 2, and then zone 3 or zone 4. So that's okay. It's quite known. It's not complicated. It's not that easy, but it's a problem that is known. It's set cover. So you want to put some points that will cover some areas, and you want to minimize the cost of the sensor and the sync that you deploy in your wireless network. So that's very classic problem. I don't know how much publications there are on that kind of deployment problem, but it's none. So that's set cover. And then we want to add the network connectivity constraints. So that becomes to be a little bit more tricky because if you look at connectivity constraint, then you have a flow problem. You need to know where to route your information on the network that you have, but your network depends also on the deployment of the sensors. So before, some decades ago, we had a trick in the wireless network community that was to say, okay, the detection range of the sensor is twice the communication range of the sensor. So that used to, this trick was has been very famous, and it allows to solve the problem with just the problem of connectivity. If your network is connected, then you have ensure also the coverage, because coverage is larger than communication range. The problem is that when you're talking about monitoring the air quality, you don't have detection range. You have a sensor that is at one point in the space, and it will sense whatever goes to its position. So you cannot have this detection range and communication range. Okay, you can still do the hypothesis that you have a nice communication range, but then you have two problems. One is the set cover problem. So you have to put some sensors so that each set is sufficiently covered, and you have to put some nodes to ensure the connectivity, to have your flow. One is a covering problem, the set cover. One is a packing problem, the network, the routing problem. And it's both kind of the two kind of optimization problems that are quite contradictory, and it gives very bad performances to solve the problem. So it gives a very ugly linear problem like this. I won't go too much into the details, but you have these connectivity problems with equations with binary variables that are, we don't like binary variables. And then, okay, you have one example with several sources that are taken from a data set around London. And then you have some performances of computing both covering and connectivity problems. But of course, it's integral linear programming, so the solving time is exponential, and at the end you cannot solve it. So we wanted to go a little bit further. The first step, it was to understand what is pollution. And so pollution, it's not really it's not a regular set cover problem. It's you have pollution that is emitted somewhere and that is spread in some zone. So you can reduce that to set cover, but you can also try to look at that as if the pollution was some kind of a signal that is sent by the pollution source. It's not a radio signal, but it's also a wireless signal. It's the pollution that is emitted and spread exactly as if you were sending a radio signal that is spread around your antenna. So in fact, you can assimilate the problem of covering the pollution source, so the set cover problem, exactly as a connectivity problem, but you have two kind of information diffusion. One is the pollution that is present somewhere, and after crossing the sensor, it becomes a packet that is sent. And so by understanding the fact that the coverage and the connectivity can be all put into the same way to express that is a packing problem in the connectivity problem, then you have very much better performances, as you see here. The right, I hope you see that. The right boxes are the computing time for the basic model with covering and connectivity that are put together but expressed differently. So it's really exponential. The second one is also exponential, but the basis of the exponential is very, very lower. So you see that you have much better running time, but also much better tightness. That means that the fact that your solution is if you want to have an approximate solution because you don't have the time to go until the optimal solution, then you will have better solution with this model. So that's purely combinatorial optimization for the problem. But that's the first step where you go from classical models coming from graph theory, and then you start to put a little bit of understanding of the physical phenomenon that you have beyond, and then you can start improving on the models and the solution that you have. And so one of the results is that there is another part of the deployment that is not addressed in this model is at what height you put your sensors. So it depends on the height of the pollution source. Of course, it depends also, and that's the first fun fact, it depends on the meteorological condition that you look at. So it depends a little bit on the seasons. On the months, you don't have exactly the same mean meteorological position. And so depending on that, you will need more or less sensors. And so, of course, if you deploy a sensor network, you won't deploy it for December and then deploy another one from January. So you need to have one that is taking all the seasons into account, and that's, again, another complexity that I won't explain that, but I will go on that further. So that's the first step. It's going from classical combinatorial problems for the deployment and the connectivity and trying to transform them to have better performances and to be able to handle larger problems. But the thing is, we don't really care about threshold detection. It was the first problem because we had that in the history of the wireless sensor community, but it's not the real problem. The real problem is to be able to compute pollution maps. So to understand how the pollution is spreading on an area, and not only to detect threshold crossing. And so that's one of the next step that we did is, okay, how am I able to build a map of the pollution? And so that's all the possibilities that you have to do air quality mapping. The first one, the easiest one to imagine, is to say, okay, I will do a lot of measurements. I put sensors everywhere, and then I will do some kind of interpolation among the sensors and get estimated maps. So that's this part. Yeah. We will look at that right after. What you can imagine is that, okay, even the interpolation, it's complicated because it's not very clear that you can interpolate two sensors that are deployed across the streets in the same way that you can interpolate two sensors that are deployed where there is a building among them. So it would be better if you have some explanatory variables coming from the background and the environment where you deploy your sensors. And then it's not interpolation anymore, but you could do some kind of artificial intelligence methods. And so that's some things that we are doing right now in the team, and I won't go into too much details for the sake of time, but we have very nice results on that. There are very good methods that come from the artificial intelligence field that are able to mix the measurements and some variables that explain the field to get better estimated maps or even prediction in the time. But then you can say, okay, there are people working on air quality for decades and decades, coming from meteorology, but also from fluid mechanics, from chemicals, from all that fields that are working on that. And so there is a lot of physical models. And so that's what I was explaining at the beginning. For the physical models, you need to have an inventory of the emissions. You need to have the meteorological parameters. You need to have some description of the urban topography. You put that on a model that computes, and then you have estimated maps. So that's the state of the art in mapping, air quality mapping today, the official air quality mapping. And then you are what we really want to do is to mix measurements and physical models. And so that what happened in the project when we working with people from the physics, we understood that their models are not only producing simulated maps, they are also producing some kind of side information that allows to do data assimilation. So you can have the simulated maps, you can have the measurements, and then you can assimilate both information to have even better estimated maps, and that's what I will explain you. So one of the first idea is to say, okay, we have the simulated maps from the models, and they output something that is very interesting. They are able to estimate where they do errors on their simulations. And we have a model of error for the sensors. So what we can do is mix everything of that and trying to say, okay, you simulate the maps, I will put sensors where you do a lot of errors and where the errors of my sensor are lower than the error of simulation, and mix everything to decrease the error of the simulation maps. And that's a problem of robust optimization because you have these boundaries on the errors. So again, I won't go into too much details of the models, but the thing is, you can understand that with this figure where you have the values that you want to have, the values of the map, and that is bounded between the maximum error, positive and negative. And so the nice part was able to link the two and say, okay, in my estimated map, my result is the measurement from my sensor, if I have put a sensor there, and if I have not put the sensor there, then I will do some kind of weighted sum of whatever is around. And then you can estimate the error with this kind of formula that is not very good for optimization, but after some computations, you can have a linear formulation of the error. That was the main contribution, is that you can put that into a linear program again, and okay, you can minimize the cost with some constraints on the error that you admit, or you can minimize the error with some constraints on the budget that you have, the number of sensors, for example, and put in the model that we had before, this robust optimization part, understanding the errors. So it works, wow. And of course, the smaller the error you admit, the higher the number of sensors that you need. It's not very revolutionary, but it shows that it works. And with that, we did many things on that, like better optimization, 3D mapping, because the third dimension is very complex, mean cost, mean error, the relaxation, whatever. I won't explain everything on that, but we did all this work. What I want to go into is, we are in a wireless networking conference. One thing is the impact of the communications range. Of course, if you have longer range of communication in your network, obviously you don't need to have the same number of relays, so you can decrease the cost of your network if you use longer range. So that's again not revolutionary. What is interesting is to link that link between the number of sensors and the of relays and communication range with the estimation error that is tolerated. Since if you optimize the error of your model and you put some constraint on the budget, the longer range that you have, the more nodes are available to be deployed optimally for the sensing. And if you have short range, then you will be forced to deploy some sensors at positions that are not good for the measurements, but are good for the relaying of the packets. And so the trade-off is there. But what you can see is that the gap is important at the beginning, but after a while, when the range are short, I mean, you don't lose a lot at the beginning. I mean, between long and medium range here, the loss is not that much, but then if you go to very short range like ZigBee, you will have some troubles. So that's one of the networking conclusion, and the other part is on the left side of the slide. It's just some methodological advice. Is when you have an optimization problem for the deployment, it's not bad to compare it to a random deployment or a uniform deployment. And here, that what you can see is that deploying uniformly or randomly, it has almost the same performances, and then the optimization is gaining a lot. It happens that sometimes the random deployment is very close to the optimized deployment. Not on this problem, but in some problems it happens, and that's where you can say that you don't need to put a lot of equation and go to another problem. But in this case, we have we have confirmed that the optimization of the deployment is really meaningful. You gain a lot by optimizing your deployment. So that's the first thing. You say, okay, well, I have my models. I know where it gives errors. So I put my sensor where there are errors. Okay. And then there is another way to do that. It's another side information that comes from the fluid mechanics models. It's not only the error, they have something that is very, very important, is the covariance of the simulation errors. And so it's where you go to stochastic optimization, and you are able to understand that it's not only that you do a lot of error there, you do a lot of error that is with a lot of variance, and then it's where you don't know anything. So it's where you should put some measurements. And then, so we can do data simulation by taking into account these stochastic informations. So it's a little bit more complicated in terms of optimization, because now you don't have your measurement that is bounded by maximum error, minimum error, but you have some kind of distribution around a mean value. But again, the good part is that we were able to linearize this kind of problem, this kind of equation, and to have some results by taking into account this stochastic informations. So it's ugly like that. But again, we don't really care. It works at the end. And then the problem is again to deploy the sensors to optimize the errors and the variance of the error. And it works pretty well. And again, we have this comparison between the deployment that is constrained by the connectivity and the deployment that is not constrained by the connectivity, short range and long range communications. And then you see that if you allow a lot of sensor to be deployed, so the cost that is big, after a while, connectivity is not a problem anymore. Your network is dense enough so that you don't really care if it's short range or long range. But if you go to a very sparse network, then you have a huge gap by constraining the deployment for the network. So of course, long range is better, but the thing is that it's we have figures on that. And then another part is, as I said, the deployment cannot be optimized only for one day. You need to take into account the variability of the seasons, the meteorological position. So then you can play with the lifetime of the network, assuming that you have batteries on the sensors, and you will schedule your sensor activity so that at each time of the year you will have the best network possible. But then you have deployed something that is useful for the whole year. So sometimes you have some kind of trade-off. You will degrade a little bit for a month, but you will optimize the number of overall sensors, and then you want to play with the lifetime by scheduling the ones that are working or not. So it's again integrating a little bit more of complexity of the problem into the optimization. So, but again, it works. At each step, I say it works, but it works with bigger computers also. That's not the problem. You want to optimize only once for the deployment. And okay, it's working also. And then what is interesting is to have this link between not only network metrics like lifetime and transmission range or lifetime and throughput, but you have then the link between lifetime and the error that is admitted by your sensing network. And so that's something interesting to link the network metrics and the problem that you have at the beginning. So you have something on the smaller the batteries, then the higher the error because the lesser sensor that you have. If you have large batteries and long range transmissions, then you have a better solution, of course. And then we try to do that real life. So that was the first sensor architecture that we did. So you can see that it's very Arduino-like. In fact, this is the microcontroller that is there. It's one of an Arduino. So first step with so different kind of sensors, storage, LoRa communication, so long range communication, and then some batteries, solar panel, etc., etc. So that's the first version of what we did. And we tried it on a field in the campus and close to a reference station from the air quality reference association, the one that are entitled by the state to monitor the air quality in France. And one parameter that is very important to go to real life problems is that you cannot do duty cycle as we used to do in a regular sensor network, because the microsensor that we have are electrochemicals, and so they have some time of convergence. And if you put your sensor idle too long, like for example, if you switch your sensor off for 60 minutes, then you need to wait 10 minutes, 9 minutes operating the sensor before it converges to a good solution. Not a good solution, but to a real measurement. So yeah, I need to. Okay, I have the panel with everything written. I don't see my slide anymore. So you have this trade-off when you do activity scheduling between the time that we need you can switch off your sensor and the time that you need to let it heat up roughly. And so if you want to do a duty cycle with 10 minutes off, then you need to wait 2 minutes before having actual measurements. So this is to be taken into account when you optimize the autonomy of your sensor with duty cycle. So that's the second part of the second version of our sensor board. So it's in fact it's still an Arduino, but it's much more optimized. And then when we did that, we were able to deploy really the sensors in the field in Lyon. So second lesson is when you do that, it's not my student that came to deploy the sensor. It's my student with people from the city that were allowed to go to the traffic light to put the sensor. So it took some time to work on. And then we have the data that comes. So that's nitrogen dioxide from one sensor. Good. And then we compare the data from several sensors and from a reference. And then we have to do what is called calibration, that is trying to take into account some drift or some offset that there is between the sensor. So the nice part is that it worked for a little bit more than 1 month or two. That's 2 weeks of data, I guess, or something like this, but it worked for the whole summer. So we can calibrate the data, but what is important is that we need to calibrate the data. And I will try to get into that very quickly at the end. And so that's just to show off the last version of the node. It's still ugly, but it worked 1 year without interrupted, only with the solar panel. It deployed on a real site. So that's to say that we can do very strong energy optimization and duty cycle optimization when working in particular with LoRa. But so that's the old solar panel, but the real solar panel that you use is a little bit larger anyway. But it worked for 1 year without too many problems. And we have still some data coming from the networks, from the sensors, and then you see also that we need calibration to have coherent measurements. And so that's the last topic I want to talk to you. I will go very fast, promise. Is the network the wireless sensor calibration? That is one of the most difficult problem for the low-cost sensors, in particular because they drift. That's the worst part. So they have errors, they have some kind of reliability problems, false information from time to time. But the worst part is that they drift. So over the time, the performance are degrading. And so that put a lot of problem, because if you want to deploy, let's say 200 sensors, you don't want to have to change them after 6 months. It's not possible. So we have to find solution for the drifting problem. And today, recalibrating an instrument is very expensive. So you take your instrument or your sensor, take it out of service, you bring it to a lab, you calibrate it, you put it back into service. So that's not doable economically, timely for a dense network. So one of the ideas is to go to in situ calibration. That means trying to calibrate the sensors without switching them off, and preferably without having to touch them. So to send someone to operate them. So doing that remotely with networks. And so that's something that we did quite recently. First, a survey on the in situ calibration strategies. Actually, there are 3 surveys that were published almost at the same time, that are very, very good, both of all of the 3. One of the 3 is ours, so of course it's good, but the 2 others are very good, it's interesting to look at. There is a lot of calibration strategies that have been published, but they are very difficult to compare together. I think I will conclude in 3 minutes on that. Just to show you some ideas of how you can do calibration on the field with networks. So here you have some kind of, it is called reference-based calibration. That means that you suppose that you have a reference instrument that you know it's calibrated, that goes close to some sensors and calibrate the sensor by exchanging information. So the way the calibration is done, I don't talk about it. It's mass, but it's not the problem. It's the way the data are exchanged and who is calibrating. So you have that, but that means that you have reference coming close to all the sensors. Then you have another way, another dream. It's kind of a graal. That is to do blind calibration. Is to think that the network is dense enough so that there is a lot of redundancy and correlation between the measurements, and so you can try to take the truth from the collective measurements and recalibrate each individual from the collective truth. But that doesn't work if all the sensors drift in the same way, for example. But if they drift in uniformly distributed direction, then it works quite well. And then there is a compromise between the two, is to have a kind of network, a graph, and then you have some reference values that calibrates some sensors, and then the calibration is propagating into the network, such as some kind of epidemic protocols, for example. Not to say about the COVID. And then, so you have this kind of strategies, and then you have also to take into account the fact that your network can be static. So what I talked about, there were static networks, but then you can imagine that they are mobile, or both mobile and static. And for example, you can have your reference instrument that goes around across all the network to calibrate everything. So that's a property of the strategies. And then you have the grouping strategies that is much more related to networking. Is you can do pairwise calibration, like one is calibrated, the other one is not calibrated. You associate the two, and then you have a calibration, and then both are calibrated, and then you play again. You have macro calibration. That means you take all the data on a centralized processing point. You do some math, and then you redistribute the calibration, and everybody is calibrated from the collective data. And then you have something in the middle, group-wise calibration, that can be linked to the fact that you have one reference calibrating a bunch of network or of sensors, or some sensors that are very close together, very correlated, that can calibrate together, and then it's another group that is taken into account. And so that's maybe I don't know, Marcello, if I have maybe to conclude there, but I think I have only 2 more slides. Just to say that when you think of calibration, you have to ask these questions. It's do you have reference values to do your calibration? Do your sensor is your sensor influenced by other values? For example, you monitor nitrogen dioxide, but the results of your sensor depends on the temperature and humidity. That's quite true for film particle, for example. You have sensors that are very tightly correlated with humidity. So that means how many sources of information you need to gather to do the calibration correctly. And then there is the mass. It's what is the form of the mathematical form of your calibration equation, but that's another problem. And this question, this one, they will strongly influence the kind of strategy that you can apply and the network that you have to have below your sensor network. So that's your example of non-translated slide, and some methods of calibration. I will let that on the slide if you want to look at that later. One thing is, if you have a network structure on your sensor, may be dynamic because your contact between the sensor depend on the time, if they are collocated someplace, or maybe the places where they are deployed are correlated at some time of the day and not some other time. Then you have to look at the fact that you can propagate a calibration around a cycle in the graph or on a subgraph, and then you have some problems that are very close to deadlock detection that is well known in many computing communities, and of course the blind calibration that exists. And just to conclude completely, all that I presented you at the beginning of the talk was on static networks, non-moving networks at least. On the calibration, I talk a little bit on mobile sensors. And then what we are doing now is, if you have microsensor, you can try to do crowdsourcing with mobility driven by people. So that's what we are doing, and that would be my last slide. All that we did goes to having smaller factor sensors, so that we can monitor the pollution moving across the city. That gives more problems. So not really networking problems, because there the communication is LoRaWAN, very long range, and it's not really a challenge there, but it's more complicated to know where two sensors can be considered they are monitoring the same thing. If we can do peer-to-peer communication between the sensor to do calibration or not. So all these problems, and the fact that we have also GPS data, that is one more question on accuracy and energetic consumption also. But yeah, that's all. I finished there. Thank you for your attention. I hope that you enjoyed going from what we did, where we were 5-6 years ago, to today, where we are really hands in the dirt, even working with sociologists to understand how the people are reacting to the information of the pollution. But then, if you have any question, I'm there.
Thank you. Thanks a lot, Hervé, for this very rich presentation. It's great to see that a simple question becomes like a crazy research ideas in terms of deployment, theoretical advances. So Very nice. I'm sure there will be a lot of questions, but to avoid overlapping with the next session and still give people some time for a coffee, let's have a couple of questions. And if you have more questions, you can send them offline to Hervé. So we still have time for a few questions. So would like to start?
Hi, Marcelo. It's me, Diogo.
Please, Diogo.
May I ask you the question?
Sure, go ahead. Go ahead.
Hervé, thank you for your presentation. It was very interesting. And I still have some question about the calibration of the sensors. When you say about when you talk about calibration, you are talking about of a post-processing function, isn't it?
Mostly, yes. It could be also maybe not real time because it's not needed to be real time, but on the fly as a distributed process, for example. One of the questions that is really open is if you do a calibration at one date, how much time you can propagate it back to correct the values that you had before the calibration. So that's also a big question.
I got it. Did you consider in this question the use of deep learning or LTSM to do this calibration? Because I guess it's not a linear function that you use as a calibration.
Yes. So I will try to get out this presentation mode. Yes. So we did not look at neural networks, LTSM, and stuff like this for the for the calibration, but for the prediction, and it's very, very similar. In fact, it will be this one. In fact, it's not the same problem, but it's a very close problem to do data prediction with AI or to do calibration. But then with the LTSM are very interesting structure of neural networks. And there is a method, I don't know the details of the method. I'm sorry, it's the PhD student, Ishraq, is knowing that. But the blue method is very efficient to do that. But we did not do the work to go to calibration with that, not yet.
I got it. Thank you for your answer. Thank you for your talk also.
Thank you.
Okay, more questions, guys. Even on YouTube, if you have questions, don't hesitate. Who else? Next. So while people think about the questions they have, in fact, I had a question about the mobility part, and how would you encourage people to serve as carrying points of these sensors? Is the idea to put them, for example, onto cars, or to put in public transportation nodes, for example, buses, or what's the idea behind this work to make this become a reality?
That's very, very interesting question. There is a group in Switzerland that is doing mobile measurement on public transportations. I think there is also the team of Bertrand Ducourtial that did a little bit of that on a bus. To my understanding of the measurement problems, measuring in mobility, motored mobility, it's very complex because you have some distortion of the pollution going from the wind, the speed, and stuff like this. So that's a field that is very interesting but complex, and there is some trials in Lyon with, I think it's the Postal Service that have put some sensors on the cars. But what we did is working with pedestrians. And so what I showed there is some maps of experiments that we did. And the thing is, we don't need a lot to do a lot to convince people to go and take our sensors and work in the city, because it's becoming a public interest problem. And so there are more and more people that want to contribute to monitoring the pollution, or to know the pollution around some specific place. I don't know where it is, but I think it's around around there. Here, there is one school that's been a very huge political scandal in Lyon because of the pollution level on this elementary school. So people are eager to contribute. And as a matter of fact, all the experiments has been stopped last year, of course, with the COVID. But in some places in the center of Lyon, we were more selecting people than asking for people to come. And some of the places, it was very difficult to find people also. But it's, I mean, yeah, I think the crowdsourcing won't be a problem, at least at the beginning, because people want to know what happens with the pollution.
I see. Very interesting. I got a message from the chair telling me that we are really we already ran out of time, because the next session has to start in 1.5 minutes. So guys, don't hesitate. If you have questions, you can contact Hervé. I suppose Hervé.
Send me an email.
An email, and people on YouTube will have the video also to learn about pollution system. So Hervé, on behalf of the organizing committee of CIoT, thank you again very much for the talk.
Thanks a lot.
I'm really sorry to stop now, but I'm under the control of the so you have an offline question from Conduc at least on the chat. So thank you again, and I'm sure people enjoyed a lot. I'm sorry for interrupting now.
Yeah, sorry for being too long.
No, that's fine. Too much information I had to deliver. Thank you very much. Thank you also, guys. You have like 1 minute break to grab a coffee, and we'll be back in 1 minute. Thank you again. See you all. Bye-bye.
And we will start with the presentation entitled Reducing IoT Bandwidth Requirements by Fog-Based Distributed Hash Tables, which will be presented by, I don't know how to pronounce the name, but Ahmad Rabay, maybe. So we will start with the video.
Hello everybody. I will present our research entitled Reducing IoT Bandwidth Requirements by Fog-Based Distributed Hash Tables. I am Ahmad Rabaya from the Department of Computer Science at Heinrich-Heine University in Germany. Our agenda at the beginning, we will start by introducing and motivating the technology and the research idea. As our research is scenario-based, I will introduce the use cases, and the simulation setup and configurations. Then I will introduce the scenarios and the evaluation of the different scenarios before we compare and discuss, and we will end with the conclusion. The first part of our introduction is Internet of Things. As you know, Internet of Things, there's a huge number of various devices which are all connected to the internet, and those devices are producing a massive amount of data that needs storage, needs processing, etc. And the statistics says that by 2023 there will be more than 30 billion devices connected to the internet. Those devices by 2022 will produce 4.8 zettabytes of data every single year, and it's even expected that those huge numbers will be overpassed in the near future because of many technologies getting more popular, like smart cities, self-driving cars, etc. Some of the examples of the big data produced from the IoT, if we look at the Boeing 787 airplane, it generates 5 gigabytes per second. And as well, those huge amount of data needs to be stored, it needs to be processed in order to get some decisions and get some facts and information out of it. As well as autonomous vehicle generates 1 gigabyte per second, and it requires real-time processing to make correct decisions and avoid any unpleasant accidents. Currently, there's a huge volume of data are handled, we can say, by either cloud computing or local storage and computing devices on those, let's say, cars or airplanes, etc. Because like traditional computing models such as cloud computing will not be able to handle those resource intensive devices because of some network bandwidth, because if all those devices will have to contact the cloud, the bandwidth will be a bottleneck and it will be a huge problem. Some of those devices, as we said, require real-time processes, and they are kind of latency sensitive applications. So if the response is a little bit late, the consequences might not be pleasant. And because of that, a new technology has been introduced called fog computing, which extends the cloud computing, as we can see here, by introducing a lightweight intermediate layer between the cloud and the edge devices. So now, instead of having this a thin, long connection between the end devices and the cloud, it's now a bit of a short, fat connection between the end devices and the fog layer. It's mostly a single hop connection, and the fog in turn will contact the cloud. The main goal of this model is to reduce the bandwidth load of the cloud, so try to satisfy as much as possible of the clients or the end users or the edge devices requests at the fog layer without contacting the cloud. This approach has been already successful in reducing the internet traffic to the cloud and improving the response time and latency. However, as we said, the fog computing compared to cloud computing can provide enhanced service qualities. But we are back at the same problem because IoT devices, because of the lack of the resources, they have to contact the cloud, and the fog devices now will face similar problems. So they are resource constraints, so they need to contact the cloud often. So if the client sends a request to the cloud, to the fog node, sorry, and the fog node cannot satisfy that request, it will eventually contact the cloud. So our proposed scenario or model or is to introduce a peer-to-peer mechanism between the fog nodes. So now at the fog layer, the fog nodes will not handle the request single-handedly, no. They can contact the peer fog nodes. So if a client sent a request to a fog node and that fog node doesn't have the resources to satisfy that request, and instead of contacting the cloud immediately, it will try to delegate some of the computations to the peer fog nodes. So the peer fog nodes, if they all, or let's say the contacted fog nodes based, depends on the, of course, on the use peer-to-peer overlay, could satisfy that request, there will be no need to contact the cloud and the request will be handled within the fog layer. As we said, this model will enhance the three-layered client fog cloud architecture by introducing the peer-to-peer in the fog layer. So it will be client, peer-to-peer fog, and cloud. And this will result in better bandwidth value compared to simple fog architecture because the cloud now will not suffer or will not be responsible for handling every single request that goes from the edge devices or from the clients. This model has been introduced and it resulted in a good improvement for the cloud node bandwidth and for the whole system, but was tested only for core overlay. And in this research, we will extend this simulation by adjusting this model for pass-through and for CAN overlays in order to evaluate and compare those different scenarios and see which overlay gives better bandwidth results compared to the other overlays. Our case study will be a simple IoT data access scenario where the pull and push functionality will be in place. So a pull request for data will go from the client to the server, and the response will push that data to the client who requested that piece of information, whether it's a fog node or the cloud itself. And here the fog servers will act as a storage unit who caches the data that comes from the cloud. So if the client will request that data again, there will be no need to contact the cloud and the fog node will satisfy the needs of the clients. Our setup and configuration, as we said, we are using a simulator. It's called perfactsim.com, and that simulator gives you lots of configuration parameters where you can configure to set up the scenario you want to run. For our scenarios, we try to keep the data at a normal volume or normal density. So we have 100 nodes. The simulation will run for 100 minutes. There will be no churn and network layer will be simple. The overlays we will use core, pasture, and CAN, and of course centralized storage overlay for the simple fog computing scenario. The application, as we said, we will use IoT data access setup. For dataset, we will have 100 data elements each of 10 kilobytes and a lookup distribution of 10 seconds, 2 seconds, and 1 second interval. And this lookup distribution, it reflects how often a client sends a new information pull request. So if it's 10 seconds, each client will send a pull request for information every 10 seconds, and for 1 second, every 1 second, they will request information. Of course, the less the lookup distribution, the more we imitate the IoT scenario. The nodes are divided into one cloud node, 10% fog nodes, and 90% cloud nodes. As we said, the fog nodes will act as a storage unit which caches the data, and at the moment, they will cache 90% maximum of the data set. So if the cache is full with 90% of the data set, random data will be deleted, and this will be one of our future work we will discuss it at the end of the presentation. To make it more realistic, we placed the fog nodes and the client nodes in Germany, and the cloud will be placed in the USA. The scenarios we are going to implement and evaluate are 4 scenarios. Simple fog computing scenario, which doesn't have anything to do with peer-to-peer. And we have 3 peer-to-peer fog computing scenarios called PAS3 and CAN. Of course, PerfectSim offers a huge number of metrics, but for the sake of bandwidth consumption, we have chosen 2 metrics that will be evaluated in this research. Net bandwidth, which shows the overall bandwidth for the whole scenario consumption in bytes per second, and the net peers bandwidth, it shows the bandwidth consumption in bytes per second for every single peer in this scenario. Let's dive in and we go into the first scenario, which is simple fog scenario. As we said, this is a 3-layered architecture, contains clients, fog node, and the cloud, and the fog node responds to the request that sends from the clients, and if it doesn't have that the requested piece of data information, it will contact the cloud. As we see in this figure, and of course the figure shows for 2 lookup distributions, for 1 second, which is in red, for 2 seconds, which is in blue. And we can see that from the beginning, the bandwidth consumption will grow, will start rising linearly, and we can see how different is the jump in the bandwidth when we change the lookup distribution from 1 second to 2 seconds. Moreover, if we look at the net peers bandwidth, we can see a similar behavior, but now we can see how are the fog nodes are handling the traffic compared to the clients and compared to the cloud. So here we can see that for the 2-second lookup distribution, the cloud is handling like 150, and then it will jump to 400. And if we look at the fog nodes, they have a different behavior. We will look at that at the table when we start comparing the results. And here we can see that mostly after the 11th node, the bandwidth will start dropping slowly, of course, with some exceptions, because it's the simulator is not perfected for computing an IoT. It's mainly a peer-to-peer scenario, a peer-to-peer simulator. So there are some exceptions, but we can see after the 11th node, which is the last fog node, the bandwidth will start to drop in a big manner. For the second, for the core fog scenario, which is the second scenario, we can see the same here for the 1 second lookup distribution and the 2 second lookup distribution. And here we have a different behavior because, as we mentioned, now the fog node will have, let's say, a main rule in handling the request that goes from the client. Of course, at the beginning, we will have a huge jump in the bandwidth because at the beginning, the caches for those fog nodes will be empty. And the more requests that go from the client to the fog node, and the fog node contact the cloud for that piece of information. When the cloud sends that piece of information to the fog node will cache that information before sending it to the client. So if any other client asks for that piece of information again, the fog node will not contact the cloud for it and can send it directly to the client. So the more time passes, the fog nodes will be able to handle more requests from the clients. And here we see as well how the cloud node and how the fog nodes handle the requests. And as we see, after the 11th node, there will be a huge drop in the bandwidth because now the last fog node is displayed and the rest are clients. For the pass-through and the CAN, it's quite similar behavior with different values. Because each of those overlays handles the requests in a different manner, but we will look at it at the end and see how we can compare the results. So those are the net bandwidth for the fog, the pass-through fog scenario, and the net build bandwidth so for the pass-through fog scenario. And for the CAN, it's as well the same, and it's the same here. We can see after the 11th node, there will be a drop in the bandwidth. Okay, as we talked about the comparison, now we can spot the difference in a better way. And as you see from this table shows the overall bandwidth consumption for the whole scenario. And here we can see that for the simple fog scenario, it's a huge jumps when we reduce the lookup bandwidth. For the code, there is a jump in the consumption as well, but it's not as huge as the simple fog. For the pass-through, the same. For the CAN, is the same. But if we are going to look for the best scenario, for the 10 seconds, the simple fog scenario is still better because it's not that resource intensive. But when we go to 2 seconds and 1 second, we can see that the peer-to-peer scenarios are giving mostly better results, especially pass-through and cord. And pass-through, it produced the best outcome in terms of the overall bandwidth consumption for the whole scenario when we compare it to the others. If we look at the bandwidth consumption for the cloud node alone, because it's the main focus for us, we can see that the simple fog node, there's a huge jumps from 46 to 160 to 400. For the peer-to-peer scenarios, the jumps are smaller, and we can see still the pass-through, it produced the best outcome in terms of the cloud node bandwidth consumption. The cord is the second best, and CAN is the third And of course, simple fog, it's the worst case scenario here. So it's kind of clear that our model gives better results in terms of bandwidth consumption. And in the future, we will try to focus on some latency sensitive application and implement better caching mechanisms in the fog nodes. Thanks a lot for your time, and please ask questions.
Thank you for your presentation, Ahmad. Now we will start with the questions. Does anyone have a question?
I have one, Diane, if I can.
Okay. Okay.
So Ahmad, thank you for the talk. Could you come back to the slides where if I'm not wrong, it's slide number 13. You have this big drop in the curve.
Just a minute. I think that Aziza must give Ahmad the presentation right, so he can present his slides.
Oh, I don't think it's necessary, but if Ahmad remembers the curve where there's this big drop around 10, if I'm not wrong, on the
I will check it. Yeah, okay. Yeah, I have it open.
Yeah, you explained. I'm not sure I got the point. And my question is, how much is this related to the simulation parameters that you used? If you change all these parameters, how would the shape of the curve change?
Yeah. Okay. Of course, the shape will change, but it will not change with that big margin. There's a big amount of unexpected behavior from the simulator actually, because as I mentioned, it's not a pure IoT or even cloud or fog computing simulator. It's a peer-to-peer simulator. But the overall shape will remain in the same, I can say, in like region of how it outperform for like reducing the cloud node itself bandwidth and put more load into the fog nodes because they are the first point of contact.
That's true. That's true. Yeah. Thanks a lot.
You're welcome.
So we have a question here in the chat. I will read so that the people who are watching us on YouTube can know the question. It's a question from Evandro. He's asking, I might miss it, but which software did you use to run your simulation? And what was the confidence interval and level you considered?
Sorry, I didn't catch the second part of the question.
What was the confidence interval and the level you considered?
Okay. Yeah. First of all, the simulator we used it's called perfectsim.com. It was developed within our research group, so it's not a commercial or very popular simulator. And yeah, our research group was mainly focusing in peer-to-peer and social networks. So I don't know about the confidence interval because it was only suggested that we use this simulator and we start using it.
Okay, so it's a deterministic simulation.
Yeah.
Anyone have another question? No? I have a question. I don't know if I missed it. One of my questions was which simulator did you use, but Evan stole from me. The second question was if there is any mobile node in your fog scenarios.
Actually, no, we didn't differentiate the clients, like if they are like computers or mobiles or etc. We only have clients who just send requests. So the clients, they are not defined. It's only any device that could send a request for a file or information. It would be considered a client.
Okay, thank you. Does anyone have another question? If you don't, I just see if there is any question on YouTube. No. So thank you, Ahmad, for your presentation. We will go on to the next one now.
Thank you all. Thank you.
So the next presentation is entitled NOOP, an IOMT system for notifying public security issues and increasing policy patrol coverage. And it will be a video presented by Camila from PUC Rio de Janeiro.
Hi, my name is Camila Lanuz and I'm going to present NOOP, an IMOT system for notifying public security issues and increasing policy patrol coverage. The other two authors of this paper are Dr. Mario Cruzendler and Dr. Flavio Pisani. This paper was written in LAC, Laboratory for Advanced Collaboration, on Computer Department of Pontifícia Universidade Católica do Rio de Janeiro. In the last few years, concern for public security in cities grew, especially in Rio de Janeiro, where this work was conducted. The population wished to be informed in real time about possible risk zones. Public security studies affirm that crimes occur when a criminal finds a suitable target at a time and a place where there is no effective protection. NOOP emerged in this scenario as a smart city initiative to support city security. NOOP offers citizens the possibility to be notified in real time about occurrences and, assuming, based on studies, that patrols are effective in preventing crimes, NOOP aims to increase the distribution of patrols in order to expand the patrolled area, leading to crime prevention. This tool is being used as a start product for the Segurança Presente 5.0, an extension of a successful patrolling initiative in the city of Rio de Janeiro. This project is already being prepared to reach the streets. A set of 3 applications, 2 for the agents and another one for the citizens, will work together with NOOP to enhance the original initiative. Tests of this app have already begun in 3 neighborhoods. NOOP objectives are optimize the coverage of patrols, optimize response time for occurrence or emergencies, notify citizens of occurrences close to him or her, notify citizens of occurrences in certain locations about which they wish to be informed. The map picture on the left shows patrol distribution without coverage optimization. Most of patrols are concentrated in the upper right corner, leaving much of the territory uncovered, including a point of occurrence. The map picture on the right shows the optimization. The patrols are well distributed to the territory, which makes them closer to possible occurrence, as illustrated. NOOP is composed of 5 main entities: NOOP Residence, NOOP Patrol, ContextNet, NOOP Monitor, and InterSCT. NOOP Residents and NOOP Patrol are distinct types of mobile users that can dynamically connect and disconnect from the system. NOOP Residents are residents and NOOP Patrols are patrols in the real world. NOOP Monitor is the service responsible for the occurrence notification and patrol allocation. The communication between the mobile elements and the service is performed by ContextNet middleware. NOOP Monitor records all activities on the InterSCT platform. NOOP has 2 pillars: group reporting and patrol allocation. At NOOP, the city is divided into areas. As we can see in the picture, each patrol and each resident are classified into groups depending on their location. Each group corresponds to an area. Due to group reporting, when there is an occurrence, only patrols in the neighborhood groups are notified. From time to time, patrol location occurs. The NOOP monitor requests the patrols go to new areas so that most of territory is covered. How all this happens? The monitor constantly receives the position of the patrols and from this information makes the allocation. The monitor also receives notice of occurrence from residents and patrols and notifies the others. Group definer patrols constantly receives the location information and from the patrols, and from this information defines to which group it belongs at that moment. The same is done for residents by group definer resident. Optimization of patrol coverage is achieved through patrol allocation. As can be seen in the picture, Area 1 is uncovered and Area 3 is with 2 patrols. When the monitor notices this imbalance, it requests that one of the patrols that is in Area 3 go to Area 1. Optimization of response time for occurrence and emergency is achieved through group reporting and patrol allocation. Group reporting ensures that only the patrols in the neighboring area closer to the occurrences are notified. The others remain patrolling. The patrol location increases the probability there will be some patrol in the occurrence in surrounding areas. In the picture on the left, NOOP is in action. The group reporting makes the patrol of the area where the occurrence happened, Area 4, be notified. In the figure to the right, there is the same situation as the figure to the left, only this time without the NOOP action. As there is no patrol location, the patrols are not well distributed to the territory, and Area 4 is uncovered. That means that in the area of the occurrence, there are no patrols. As there is no group reporting, all the patrols are necessarily notified, and they have to leave their patrol stations to attend the occurrence, leaving several regions uncovered. Notification of citizens about occurrences close to him or in certain locations about which they wish to be informed is achieved through group reporting. In the picture, we can see this notification occurring. The resident who is in Area 4 is notified for being in the same area as the occurrence, and the resident who is in Area 2 is notified because she subscribed to receive the occurrences from Area 4. The patrol allocation algorithms have 2 main functions, and both receive a parameter with the list of patrols in operation. Calculate new patrol area returns the next area to be patrolled by a unit, and the patrol allocation checks if there is a patrol that needs to migrate, and if so, return this patrol and new area to which it should be assigned. The patrol allocation algorithm is flexible and can be re-implemented through city area interface. To test NOOP in a simulation environment, some algorithms have been developed and will be presented below. It's worth mentioning that NOOP is extremely flexible and was designed so that the patrol allocation algorithm is as suitable as possible for each particularity of territory and city. The effectiveness of different algorithms in different territories can be tested through NOOP. The tested algorithms of this paper are further distance, nearest distance, and increased coverage. The further distance algorithm, or NOOP-FD. In this algorithm, the calculate new patrol area function returns an area A such that the sum of distance from A to the patrolled area is maximum, as shown in the picture. That means that the area A is the furthest area from the patrols, and that the response time will be the longest for an occurrence in area A. Therefore, placing a patrol in area A decreases the response time to occurrences that might happen in or around it. In further distance algorithm, the patrol allocation functions uses the calculate new patrol area function to find the area to be assigned. In example, area A. The patrol allocation so preselects a patrol P such that the patrol P will take the longest to move to the other areas. In example, patrol in area 1. The algorithm so decides to make the migration if area A, in case 15, is closer to other areas, the area of patrol P, in case area 1, preserving so the other areas from being uncovered by the migration. Therefore, placing a patrol in area A decreases the response time to occurrences in most of the areas. The nearest distance algorithm, or NUP-ND. The calculate new patrol area function is the same as the calculate new patrol area function of NUP-FD. The patrol allocation function uses the calculate new patrol area function to find the area to be assigned. The patrol allocation pre-selects a patrol P such that the patrol P is the closest to A, in case patrol in area 5. Doing so, it reduces the time spent moving between areas. The algorithm decides to make the migration if area A, in case area 15, is closer to other areas than the area of patrol P, in case area 5, preserving the other areas from being uncovered by the migration. Therefore, placing a patrol in area A decreases the response time to occurrences in most of the areas. The increased cover algorithm, or NUP-IC. The areas covered by a given patrol is defined as the areas where the patrol is located and the ones that are adjacent to it. In the figure on the left, the areas covered by a patrol in area 11 have orange circles, and the areas covered by a patrol in area 1 have green squares. The NUP increased cover algorithm seeks to maximize the cardinality of the set of areas covered by patrols. Doing so, there will be more areas with neighboring patrols or patrols that are a short distance away. Therefore, the NUP-IC decreases the response time to occurrence in most of the areas. The calculate new patrol area function returns the area A that maximizes the cardinality of the set of coverage areas. In case of the right figures, the area A would be the area 6. The patrol allocation algorithm function uses the calculate new patrol area function to find the area to be assigned. In example, area A. The patrol allocation pre-selects a patrol P such that the migration of P maximizes the cardinality of the set of areas covered by all patrols, in case patrol in area 5. The two small right figures show the two possible patrol migrations, from patrol in area 5 and in area 16. The migration from 5 makes a bigger cardinality, so 5 is just chosen one. The patrol allocation decides to make the migration if the cardinality of the set of coverage areas after the migration is greater than the set without. In the figure's case, the migrate must be done. The NUP effectiveness tests. The objectives of the test are verifying the effectiveness of adding group reporting and a patrol allocation algorithm to a patrolling system. The metrics used were temp R, the average time between recording an occurrence and all patrols arriving at its location. It measures how much faster is the response to an occurrence with NUP. Temp FR, the average times between the recording an occurrence and the first patrol arriving at its location. It measures how much faster is the first response to an occurrence with NUP. F patrol, the rate of the time of the operation in which a patrol is effectively patrolling, not on the move or resolving an occurrence. It measures how much effective patrol time is gained with NUP. To compare the effectiveness of NUP in different patrols configurations, we test two different size territories. One simulating 16 square kilometers split into 16 areas, and another one simulating 25 square kilometers split into 25 areas. This 25 area simulation represents a scenario of great scarcity of resource when compared with the first, given that a larger area is patrolled by the same number of units, in the case 4. 5 different NUP configurations were tested. DB1, the first one, without using any NUP functionality. GR, using group report only. GR plus FD, using group reporting and NUP FD. GR plus ND, using group reporting and NUP ND. GR plus IC, using Group Report and Noob IC. We analyzed all scenarios for the 16 area region and, for simplicity, W1, GR, and GR plus EC for the 25 area regions. 2 scenarios were designed, each one consisting of a list of 15 work periods with 8 random occurrences. The graph shows the effectiveness test results we obtain for the average arrive time of all patrols, 10 par. We consider cases such as 16 area scenario 2 and 25 area scenario 1, where adding group reporting by itself or along with an allocation algorithm improves TEMPAR. However, there are also cases such as 16 area scenario 1 and 25 area scenario 2, where W1 presents better results. As we can see in the table on the right, when considering all tested 16 area scenarios, we observed that in 68% of the cases, GR were faster than W1. In 68% of the cases, GR plus FD were faster than W1. In 70% of the cases, GR plus ND were faster than W1. In 78% of the cases, GR plus IC were faster than W1. For the 25 area tests, we see that in 58% of the cases, GR were faster than W1. In 89% of the cases, GR plus IC were faster than W1. This graph shows the results for the F-Patrol metric. Using Noob increased F-Patrol in all tested scenarios when compared to the W1 baseline. In particular, we highlight GR plus IC for the 16 area region, which reached 52%, while W1 presented only 13.8%. For the 25 area region, FF Patrol for W1 was 80.7%, and we see that adding simply GR or GR plus IC more than triples the percentage of the time the patrols are in operation. The Noob scalability test. The objective of the test is checking the responsiveness of Noob monitor in cases where there is increased occurrence frequency. The tested frequencies are far above those verified in the real world. The metric used was the noob time. The noob time is the interval between the monitor recording the occurrence and sending the message to the patrol groups. In a scenario where noob needs to handle a lot of data, the point of the system that would be stressed the most would be the monitor. Monitor is the main element that must be tested to evaluate the scalability of the system. The graph shows the results of the scalability test. The vertical axis shows the average time interval between the occurrence in record and the dispatch measured in milliseconds, with the error bar indicating the standard error. The horizontal axis shows the occurrence in periods, from 100 to 5 milliseconds, first with 10 and then with 30 occurrence messages. Each point corresponds to one of the tests. We observe that regardless of the frequency of occurrences, the process takes between 100 and 200 milliseconds in almost all cases, except one outlier, which could have been caused by changes in the network condition. Noob is effective in reducing the response time of occurrences and in increasing the effectiveness of patrolling. Relocation algorithms should be elaborated according to the characteristics and size of the region, and Noob architecture makes it easy to do it. Group notification proved to be an important feature, as it alone was able to reduce response time and increase the effectiveness of patrolling. The authors thank CAPS and FAESP for the financial support and the INTERCIT for the technological support.
So, thank you for the presentation, Camila. Does anyone have any question?
I have a question. That's me, Diogo. Hi, Camila. Thank you for your presentation. I still have a question about the comparison of your work with other proposals for the same problem, because I see that you compare your work with other proposals of yours. So how do you compare it with another concurrent proposal?
Um, Let me see if I understand your question. You're asking how we could compare our proposal to other problems that we see or that we find in literature, right?
Sure.
Yeah,
Yeah.
there was it was a little bit hard to find this kind of problem in other situations around the world because we use our situation in Rio de Janeiro as an example. In other parts of the world, they use camera to increase security. There are other technologies being used. There are there are other things that they are looking for to increase security, not only petrol location. We find some studies more theoretical in actually looking for political security studies, not technology studies, to embrace our ideas as base our ideas. And so it's a difficult question. I don't know how to direct it because it was hard to find similar initiatives because this is really particular to a situation we live in Rio de Janeiro. And so I think like we tried to propose a solution that was that that could be used in different territories. Like so, I think that we could possibly measure and compare our solution not by the metrics that we proposed, by but sorry, but looking to other initiatives that could lead to increase of public security, not only patrolling, other things that could complement it. Looking directly to what we did, it was hard to find something to compare.
I understand what you say. That is kind of situations typically from Rio de Janeiro, where you cannot use cameras or other things to do. So it's hard to compare with other solution that we see in the literature because they use other technological means.
Support, yes.
I got it. Thank you for your answer.
Nothing.
So we have a question from YouTube. It's from Ricardo Moura. He's asking how the location with many occurrences are considered, and he removed the question before I read it. So just a minute. While he is putting it back, if he wishes, I don't know if he will put it back, but I have a question about how you stated your problem. It looks for me that it's kind of an optimization problem, but I don't think you did like an optimization. Is that right?
Yes, right. It looks like optimization problem, but our study was more in the. We are thinking more of delivering a solution that could be used to studies that aim to optimization. Our algorithms, as we put on our paper, were when they were not based in the literature. We delivered a system that could be used for studies that aims to optimization. What we call optimization is like we base this on studies of public security that say that having a patrol nears you increases the security of the area. So basically, this was our we based it on this idea as an optimization idea. So there's no studying directly to the what optimization means. So there, this part of the paper. I think it could be continued. So, but we intend to build a solution that could be used for it to study better ways to optimize the distribution in the territory.
Okay, thank you. So he's asking, how did you consider the place with many occurrences in calculation?
I'm sorry, I didn't understand the question. Could you repeat, please?
How did you consider the places with many occurrences in your calculations? I'm not sure what he's asking about, but I think he may be thinking about if you consider. Let me think. How did you take in consideration the number of occurrences that happen in each place? Like, is a place with many occurrences more? Did you consider that it will take more? It will need more patrolling, or I don't know. Maybe it's something like this.
I now I understand. Like the heat map of the occurrences.
Yes.
If there's this study of the territory was not embraced in our work. Our distribution of occurrences was totally random for the tests.
Okay. And I have one last question. I don't know if anyone has one. Does anybody has one question? If you don't, I have a last one, so we can finish our this presentation and go to the next one. I would like to know, I don't know if I missed it in your results, but the time the algorithms take to converge to a solution, is it like real time, or does it take some time to get the best solution for that patrolling?
Let me see if I understand. You were asking if we measure the time that the monitor spends to calculate a new allocation.
Yes.
No, this wasn't. This time, we didn't measure that. The only thing that was measured as a scalability problem in the scalability test was the time that the monitor takes to distribute the occurrences, not the time that used to send the request to move from one area to another. But let me see if I understand wrong. This time that you're asking about is the time that the patrols spend moving, or the time that the monitor takes to send the request?
Yes, the last one, the time that the
last one
takes to send the request.
This one we didn't measure.
Okay, maybe you could measure this for the scalability problem, because if there are a lot of patrol policies, maybe it will, it's like everything that must calculate paths always takes a long time when you have a lot of nodes. So the nodes are the policy officers, and maybe this will be this will bring some kind of scalability problem that we'll have to tackle in the future.
Yeah, I agree. This is an interesting thing to measure, of course.
Okay, thank you for your presentation, Camila.
You're welcome.
So we will follow to the next one, which will be presented by Silvio from Fluminense Federal University. It's called GRASP, Based Features Selection for Intrusion Detection System. for intrusion detection in CPS perception layer. So we'll play the video now.
Hello everyone, my name is Silvio. I will present to you this paper named A Graph-Based Feature Selection for Intrusion Detection in Cyber-Physical Systems Perception Layer. The other authors are Diego Passos, Sarah Albuquerque, Daniel Mossé, and Luis Oshie. So cyber-physical systems already received several industrial IoT systems, for example, manufacture and power industries, such as this figure that illustrates substation systems. And in these systems, security is very important, especially the resilience of such systems to attackers. And in the past recent years, many attacks were reported targeting the power systems, nuclear plants, airplanes, electrical vehicles, and other related domains. So to stop these malicious activities, it's very important to employ some intrusion detection systems. These systems play a crucial role in cyber-physical system security. And the effectiveness of the systems depends on the detection, timing, and accuracy. And feature selection methods help to improve both goals. We can increase the detection accuracy by discarding irrelevant features or redundant ones, and as a secondary benefit, we can reduce the feature subset. That means to have less data and faster processing to process all this data. So this work investigates how feature selection techniques may improve intrusion detection accuracy in the cyber-physical systems, specifically in the cyber-physical systems perception layer. So in particular, we propose a grasp-based meta-heuristic implementation for feature selection. I will talk about grasp in the next slides. So basically, these methods run offline to pre-select important features. After this pre-selection, we perform the online IDS, intrusion detection system. And basically, the result reveals that our implementation outperforms the accuracy of traditional filter-based methods. I will talk about this in the next slides. And it's about to 17.25% on average of improvement by using grasp-based feature selection rather than filter-based traditional methods. So this is the big picture of a cyber-physical system. We can divide it in three main layers. The first one is the physical world, and the third one is the cyber world. And in between these layers, we have a transmission layer that is basically composed by transmission technologies to communicate data from physical or cyber worlds. And specifically in this physical world, we can have many smart objects that have devices such as sensors or actuators, and these devices are prone to a lot of attacks. In special, we will address three main attacks that can be launched to target this layer. These attacks are both variations of DOS or denial of service attacks. The first one is flooding. In flooding, basically the attack will send a large number of advertising cluster head messages. That's a typical message exchanged in the leech algorithm that is shown in this figure here, where we can have a lot of sensors, and these sensors send data to the CH, that's the cluster head, and each cluster head from each cluster will synchronize its data to the base station. So basically, each cluster will send a large number of messages to other sensors, to become a cluster head. And this is the flooding attack. This message will be sent in a high transmission rate and a large number of messages. After a malicious node becomes a cluster head, it can launch two other attacks that are black hole and gray hole. In the black hole attack, the attacker advertised itself as CIoT, as I told you before, and after became a CIoT or a cluster hole, it will drop all messages. So basically, all the other sensor nodes will send it data to cluster head, to it be sent to the base station. However, as it is an attacker, it will drop all the messages. So in the black hole, no messages are sent to the basic station. And similarly to this attack, the gray hole is also, the CH is also compromised by an attacker, but instead of to drop all the messages, some particular messages are selected to be sent to the base station. So if we employ an IDS, for example, at that place, we will verify that it's still receiving some messages from the other sensors, the legitimate sensors, but part of this message will be discarded by the cluster head. So talking about the detection methods, we can split all the detection methods in host-based or network-based methods, and we can also have different algorithms that can be employed to detect intrusions. So in our particular case, we will use both features from the host level or application level, and also network-based features that relate mainly in traffic features. So we will analyze both these features, and we will use 5 different classifier algorithms to detect when sample represent an attack or benign activity. So talking about the related works, we have GRASP, our main related work. That's the iterative multi-start meta-heuristic proposed to solve graph planarization problems. But also after that, other works used this algorithm, the GRASP algorithm, to generalize it to solve another combinatorial problems. So feature selection can be considered a combinatorial optimization problem, and as well other similar problems, GRASP can be applied to solve it. So all these works does not, they don't deal with intrusion detection in cyber physical systems, IoT, WSN, or in general intrusion detection in any other domain. They just perform feature selection, but to other domains. And there are another works, in particular this reference, that apply GRASP to intrusion detection contexts. However, they apply it to traditional networks that is different from cyber physical systems or WSN, wireless sensor network. So in this work, we perform an assessment of a GRASP-based implementation as a novel combination of RCL. I will talk about RCL that in the next slides, and we'll use a novel combination of RCL, classifier algorithms, and local search. So basically, we will use particular components to implement a new GRASP-based algorithm based on the traditional algorithm, but with a few new components. And we also explore a new domain, that is cyber physical perception layer. So this is in the green box, the GRASP algorithm, and we have 2 main phases in the algorithm. So we will run in many iterations these 2 phases, and the first phase is basically to construct a solution, and after this construction we will have a greedy solution, greedy feature selection or feature subset, and based on this initial solution we will perform a local search to try to improve this solution, that is to achieve a better solution or that have a better accuracy, because accuracy is the main metric to evaluate the goodness of each solution. So in this yellow box we have the construction phase, and that is basically we will employ a filter-based method that is information gain or IG, and after employing this method we will rank all the features available to select the top 20 features, for example, or top N. This number of features to compose the RCL, that is restricted candidate list, can be parameterized. So after to have a list of the top ranked feature, we will select randomly some features from the RCL to compose an initial grid feature selection subset. So we can choose, for example, number 5 to the length of this feature subset. So from these 20 features, for example, we will iteratively select random features until compose a feature subset of 5 features. After that, we will use this generated solution in the other phase, that is local search, and in the local search we will perform some neighborhood algorithm to disturb the solution and derive similar ones, or that means to exploit the neighborhood. And basically we will perform in this case the bit flipped algorithm, that is randomly choose one feature from the RCL and put it in our feature subset solution, and also we will remove a current feature from the current solution, and we will keep the same cardinality of 5 features. So this is a better representation. It's a graphical representation of both construction phase and local search phase. We will start having an RCL, and after this RCL is generated by filter-based algorithm, we'll construct a random solution. We will evaluate that solution with some classifier. In our case, we will employ multiple classifiers, so we will run all these proxies multiple times to evaluate it. And after this evaluation, we will choose the best solution to compose our final solution of the grasp algorithm. So basically, after evaluating, we will verify if it is the best solution, and regardless the best solution, we will send it to the local search phase. So we will perform here some movements like I told before, exchanging features from RCL and the current solution to generate the neighbor solution from this neighborhood. We will evaluate these new solutions, and we will output the best solution after a predefined number of iteration. All this process also is run many times until we search a criteria that is a max number of iterations. So basically, to experiment this algorithm, we will set up a grasp implementation, and we define as maximum iteration the number 5th, and 22 local search iteration. So basically, we will have 50 full iteration, and for each of these iteration, we will have 20 local search iterations. And also, we choose the RCL as the full available features, because the WSN dataset that we used in this experimentation already have just this number of features. So to avoid discard many features, we will keep all these features as the RCL algorithm, as the RCL features list. So our grasp algorithm will take all these features as initial RCL. So the size of feature was set to 5, and the final solution accordingly will have 5 features. And as local search, we employ the bit-fit algorithm that basically exchange features between the RCL and the current solution. So as a result, we can see that when we use the filter-based algorithm, information gain ratio, or on-air, for example, we have a fixed feature selection for all the classifiers, because this technique does not consider which classifier will be used. So it's not the best choice because as we can see here, when we use grasp for each classifier algorithm, there are different features selected to compose the best feature selection subset. So basically each number here represents a feature index, and the description of each feature are listed here. All these features are captured from the WSTN dataset. So as a result, we can see that for black hole attacks, GRASP enabled the classifiers to reach an accuracy of 99.99%. That's the most high accuracy. That is the first bar compared to the on-air and IG and GR. That's information gain and gain ratio. So when we compare GRASP-based feature selection, we can see that the accuracy is significantly improved to black hole attacks. Regarding flooding attacks, we can see that GRASP is also never worse than IG, GR, or on-air feature selection. And finally, to gray hole attacks, we can see that the GRASP achieved an accuracy about 99.9% for all classified algorithms except to naive Bayes. As I told before, this attack can be considered the most challenging attack because as the attacker performs selective discarding, it's the behavior of its attacks is harder than the black hole or flooding attacks to detect. So as conclusion, we can see that perception layer of cyber physical system and IoT systems have some tiny devices, and these devices are particularly susceptible to threat due to their strain constraints, and planning and designing of a security CPS are important, but using IDS is essential because many times it's not possible to stop all the attacks before they occur. So we need to use some IDS to take some action when a new attack is occurring, and this attack may be not predicted at the planning and designing phases. So feature selection is very important. It's a very important approach to obtain accurate attack detection and a timely attack detection. Also, we quantified how GRASP-based feature selection implementation can improve the accuracy of 5 classifiers to detect black hole, gray hole, and floating attacks, targeting the cyber physical system, specifically the perception layer. So, in summary, we can see that GRASP was able to increase the detection for all attacks, up to 31.8 for black hole, 12.26 for gray hole, and 7.70 for flooding attacks. On average, it provided an increase of accuracy and about to 17.25% more than other filter-based feature selection. So it's all. Thank you, and I will pass some slide with some reference, but in our paper we can see more details, and now I believe it's open to questions. Thank you.
Thank you, Silvio, for the presentation. Does anyone have any question?
I have a question. Thank you, Silvio, for the presentation. I still have a couple of questions about the idea that you use to create to do the feature selection. First of all, you say that you have a local search and also a part that you call grasp construction. This part that you call grasp construction is a global one that runs globally, isn't it?
Yeah, sure.
And how do you do to meet, in fact, not to meet, but to compose features that you select from local search with others that may be completely different? In fact, you may have in the global one the entire group of features. How do you weight which feature goes to the global model?
Right. So basically, at the construction phase, we will construct a RCL, a restricted candidate list that is all the pre-selected features, and this pre-selection is based on our filter selection algorithm, such as RG or GR, like I showed in the presentation. But all this RCL will be used both for the construction phase and the local search phase. However, the features that will be selected to to build the first initial solution will be discarded from the RCL. So my RCL will be updated, and a shorter RCL will pass to the local search phase. So I will have just the features that is not it's not belong to the initial solution available at the RCL. After this iteration, I will put this feature again to the RCL, and when I start a new global iteration, I will have all the RCL complete.
Yeah, but when you do like this, you may have all the features on the global search, isn't it?
Yeah,
What makes the local search kind of useless in some case, or not?
yeah. So basically, in the local search, I will have a seed that is the construction phase feature selection subset. So I will work on the local search phase under some particular movements. So basically, the solution will be like the previously, but with some particular movements. It will be similar or neighbor solutions. And the
Okay.
construction phase, I will build a random, entire, completely different feature subset.
Okay. And the other question that I have is about the metric that you use to measure the goodness of each solution. In fact, you say that you use accuracy, but why not use precision or some other measures in order to have a better solution for the attacks? In fact, you are much more interested in the attack than the normal situation. So why not precision?
Yeah, it's a very good question, and included we detected after finished this paper that we can choose, for example, F1 score for have a better model. So we are planning to do another paper, an extended version, and we will consider mainly the F1 score, including precision, recall. But yeah, you are right. The accuracy is not even the best solution, specifically when we have an unbalanced data set. So
That's
yeah,
it.
that's a good point to improve this paper.
Thank you very much.
Thank you.
So we have time for one more quick question before we go to the break. Anyone? Let me see on YouTube if there is anyone. No? So I will ask a very quick question, in fact.
Okay.
Did you measure the computing time of your algorithms?
Yeah, this is not the main focus on this paper, but we observed some the timing of these algorithms. For example, we detected that random forest is much more time expensive than other algorithms. So sometimes we can see that the execution time of the algorithm can limit the best solution because we will have the iteration will take more time to be completed. So, for example, if we consider the maximum time of all grasp running process, when we use time-consuming classifier algorithms, we can have a low performance of grasp. So yeah, basically our computational time will depend a lot of the which algorithm classifier algorithm is performed. Grasp in general is not too much time consuming because it's a lot of iteration and simple movements. But the time of detection for each algorithm will really impact it because we use 50 full iteration and 20 local iteration. That is a 1,000 of full grasp iteration. So it's 1,000 times the number of a single evaluation of one classifier.
Okay, but you said that random forest is the worst one, right? In terms of execution time.
Yeah.
This time that the worst one takes, do you think that it may impair the feasibility of the ideas or not?
Yeah, sure. If you consider, for example, in this case, it is not impacted because we set the stop criteria as the maximum number of iteration. So, for example, we can see that when we're running with random forest, we take a lot of time, so, a couple of days to running to complete the running. And for example, when we use the naive base, we can finish the grasp less than one full day, less than 24 hours, for example, to achieve this number of iteration. So if you use the maximum time as stop criteria, we can see that random forest will stop before it can achieve a best solution because it cannot be explored all the neighborhood.
Okay, thank you very much, Silvio.
Thank you.
We'll go to the break so we can maintain our schedule, okay? And in about 5 minutes, we will be back.
Hello, everyone. My name is Diogo Matos. I'm a professor at the Universidade Federal Fluminense, and I'm the chair of the next session, the demonstration session. And for now, we're going to start with the first paper of the demonstration session called Path Recovery Algorithm Using Fast Failover for Software-Defined Networks. The paper is authored by Ian Vilar, Vinícius Ferreira, Débora Muchaluat Saad, Célia Albuquerque, Igor Monteiro, and that's it. Let's start with the presentation. We're going to present, I guess it's Ian. Thank you all.
Hello everyone, my name is Ian. I'm currently working at MediaCon Lab of Fluminense Federal University, and I will present the work entitled Path Recovery Algorithm Using Fast Failover for Software-Defined Networks. In several telecommunication scenarios, the communication between hosts must be ensured, even in the presence of failures in the telecommunication infrastructure. Power substations protect their systems through the exchange of protection and control messages in the telecommunication infrastructure. These messages are responsible for isolating faults in the electrical system and preventing more damages. These messages may have strict time constraints in the order of 3 to 20 milliseconds, like goose and SV, and less strict time constraints in the order of 100 to 1000 milliseconds, like MMS. Here we have an example. Assuming that the teleprotection equipment in substation A has measured a deviation in the electrical voltage or current, it will send a goose message through the telecommunication system to the substation B. The teleprotection equipment in substation B will receive the goose message and will trigger the protection equipment to perform damage prevention, such as opening the electrical system. The goose message sent by substation A to substation B cannot be lost and must be received within its time constraint. Therefore, this work's goal is to propose a loop-free fast failover recovery algorithm for software-defined networks in the context of power substation smart grids. The proposed algorithm computes and configures unicast primary and backup paths using fast failover open flow groups and flow rules to ensure no packet loss when a link in the primary path presents a failure. To test our solution, we have implemented it in the ONUS controller and evaluated it in a teleprotection-based scenario. Our solution is also able to avoid loops when configuring the flow rules and fast failover groups. As SDN foreign devices have only the local neighborhood view, they are not able to know that has a failure in one link or device in the primary path that's not its neighbor. In this sense, it's not sufficient to just avoid the failed link or device in the backup path configuration. To switch from the failure, we use fast failover groups. Fast failover groups are composed of action buckets and have the goal to provide alternative paths to forward packets in the presence of failures without the switch controller communication. The fast failover group maintains an ordered list of action buckets, in which only the first bucket that has a port live in the list is activated. To illustrate the looping problem, let us assume that host 2 will send a packet to host 1, and S4, S3, S1 is the primary path, and S4, S2, S1 is the backup path. Host 2 starts transmitting, and the packet is received by S4 and S3. S3, you'll notice that the link to S1 is down, and therefore, the second action bucket in this scenario will be activated. The second action bucket in the fast failover group is to transmit the packet back to S4. But S4 does not know that there is a failure in the path for S3 and the first action bucket in the fast failover group is still alive. Therefore, S4 will send the packet again to S3, forming a loop. We solve this problem by tagging the packets as a second action in the fast failover action buckets. The first action bucket tags the packet with a VLAN ID configured for the primary path and send the packet through the primary port. The second action bucket tags the packet with a VLAN ID configured for the backup path and send the packet through the backup port. In this way, the device that has a failure in the primary path can inform upstream devices that the backup path must be used. To illustrate how the solution works, let us assume the same scenario as before. When S4 receives the packet, it tags the packet with VLAN ID for the primary path and sends the packet to S3. S3 will notice that the link to S1 is down, the second action bucket will be activated, the primary VLAN ID will be removed, and the backup VLAN ID will be inserted, and S3 will send the packet to S4. This time, S4 will know that the primary path is down and will send the packet to S2, and the packet will be delivered to the destination. Another problem that may cause loops in the network is the configuration of independent primary and backup paths. In this case, when the backup path for two different switches passes through each other, the packets will be stuck in a loop. This figure illustrates in opaque arrows the primary and backup paths calculated for S2, and the other arrows the primary and backup paths for S3. As we can see, the S3's backup path passes through S2, and S2's backup path passes through S3. When link S2, S1, or S3, S1 fails, the second action bucket of one of the two devices will be activated, and the packet will be stuck in a loop between S2 and S3. In our solution, just add devices belong to both primary and backup paths. Devices that belong to the primary path are responsible for backtracking the packets when a link or device fails. The device connected to source host is responsible for rerouting the packets from primary path to backup path. The proposed algorithm configures a pair of unicast primary and backup paths between a source and destination to ensure no packet loss in 3 steps. First step configures the device connected to the source host to reroute packets from primary path to the backup path, and the device connected to the destination host to remove the VLAN header before delivering the packets. The second step configures devices that belong only to the primary path to deliver the packet when there is no failures and to backtrack packets when failures occur. Third step configures devices in the joint backup path to deliver packet tagged with backup VLAN ID to the destination. The algorithm for the first step works as follows. If the device is connected to the source host, we get the primary and backup ports and create the fast failover group. In the primary action bucket, we state actions to push the VLAN header with primary VLAN ID and to forward the packet to the primary port. In the backup action bucket, we state actions to push the VLAN header with backup VLAN ID and to forward the packet to the backup port. Thereafter, we create the flow rule that will point to the fast failover group. Select the packets for the specific source and destination rules must be processed by this flow rule, and point the flow rule to the fast failover group. At last, we create the flow rule responsible for the rerouting. We select the packets for the specific source and destination tagged with backup VLAN ID, and they must be forwarded to the backup port. If the device is connected to the destination, we create the flow rule to remove the VLAN header and to deliver the packet to the destination. In the second step configuration, we create the fast failover group and state the actions of the primary action bucket to set the primary VLAN ID and forward the packet to the port of the primary path. And state that the actions of the backup action bucket to set the backup VLAN ID and forward the packet back to the port where the packet was received. Thereafter, we create the flow rule that will point to the fast failover group that is responsible to start the backtracking in case the device faces a failure. At last, we create the flow rule responsible to backtrack the packets in case the device receives in the primary path a packet tagged with the backup VLAN ID. And finally, the algorithm for the third step configuration just configures in the device belonging to the backup path the flow rule to forward packets tagged with the backup VLAN ID toward the destination. We analyze the performance of our solution, assuming a power substation smart grid scenario. In this scenario, we have a pair of source and destination hosts in which the source host transmits message 1,840 bits long in a 78 microseconds inter-message interval. The communication infrastructure is composed of 20 devices disposed in a ring topology, with 100 megabits per second links and 10 to the minus 4 propagation delay. And we compare our solution to a reactive recovery approach, in which ONS reconfigure the network only when it's aware of the failure. As we can see in this graphic, we evaluated the round trip time over the transmission of 100 packets. The vertical dotted line in the proactive recovery graphic shows the exact moment that we failed the link. We have chosen to fail the link that resulted in the worst case scenario, the last link in the primary path. In this way, the packet needs to be backtracked over all primary path again to the device connected to the source host and travel all the backup paths to the destination. As we dispose the source and destination hosts diametrically opposed in the ring topology, the packets in the proactive approach travel the entire topology and a half after the failure. And even in the worst case, all packets respect the imposed time constraint by SV protocol without any loss, and the reactive approach lost 9 packets, the time needed for ONS controller to reconfigure the path. To conclude this work, we have proposed a loop-free using fast failover recovery algorithm for SDN using only vanilla OpenFlow. The evaluations carried in a substation smart grid scenario show that even in the worst case failure scenario, our solution is able to deliver packets without loss and respect the 5 milliseconds time constraints.
Thank you, Ian, for your presentation. I would like to know if somebody has some question about this presentation. Questions? No question on YouTube. So I will make some questions, a couple of questions. Ian, you say that SDN devices do not have only have a local view of the links. What do you mean about it? Because SDN intends to have a global view of the network. So why not to use this global view of the network?
Hi, Diogo. Thanks for the question. I mean as local view because switches in this case are all controlled by the controller, and to use the controller to configure in the moment that the links fail, we'll have some packet losses because of the time to compute the new path, as we show in the results. So we use pre-configured flow rules and open flow groups to switch from the link that failed to a new path that will deliver the packets to the destination in the moment of the failure, without the controller to need to compute a new path. The path is already computed and installed in the switches.
Yeah, but I didn't get the idea of changing the VLAN. In fact, when you have to change the VLAN, you will need some action about the controller, isn't it?
Sorry, I didn't understand. Can you repeat the question?
When you change the VLAN ID to use the failover path, you need some action from the controller, don't you?
No, because the VLAN ID is already configured in the flow rules as the backup path, and the action buckets change the VLAN ID to use the primary path when there's no failure, and when the switch detects a failure, it changes to the backup VLAN ID, so the other switch know that they must use the backup path.
So in fact, your limitation to use vanilla OpenFlow is because of this kind of bucket actions, isn't it?
The vanilla OpenFlow, it's because there's some works in the literature that use open state and other modifications of the OpenFlow that usually the industrial equipment don't use. They just use vanilla OpenFlow. So we chose to use just flow rules and OpenFlow groups because they don't have any others features that the literature proposes.
Okay, thank you. Any other question on YouTube or here in WebEx? No question. So let's thank Ian for the presentation. Thank you, Ian,
Thank you.
and let's go to the following presentation from Sofia Correia Santos, who is going to present an IoT rainfall monitoring application based on wireless net communication technologies. Thank you.
Hello, I am Sophia, and this is an IoT rainfall monitoring application based on wireless communication technologies. I made this work with Diogo Matos, Ricardo Firmino, and Gianni Medeiros. We are all from the Telecommunication Engineering Department at UF in Brazil. Remote rainfall monitoring is an important IoT application for developing strategies to plan city area better, reducing the risks of disasters and mitigating social and economic problems resulted from heavy rains. In several governmental hydrometeorological stations in Brazil, the data collection is done locally in a manual or semi-automated fashion. There are stations enabled for remote collection, but data is transmitted through mobile or satellite networks. The main drawback of using such networks to transmit data is the dependence on third-party infrastructure, which incurs additional operational costs. Our goal is to develop a low-cost hydrometeorological monitoring station that we are going to monitor the rain. And the other goal is to do a performance comparison of Wi-Fi and LoRa communication technology when they transmit the collected data from the rain gauge. Our purpose is to build an IoT application for rainfall monitoring independent of third-party infrastructure for data transmission that integrates a digital rain gauge to a wireless communication module and allowing to automate the data collection and transmission to a processing storage server. We propose a hybrid architecture based on short and long-range communication, and we also integrate our prototype to an IoT platform to facilitate data management and visualization. We propose a hybrid architecture that envisions the communication of a dense pluviometric network using short and long-range communication technologies. The architecture has 3 layers: sensing, where resides the digital rain gauges responsible for collecting data; gateway, which is responsible for providing the adequate communication technologies to communicate servers and sensors; and local processing and storage, where the servers are deployed, one for each region of interest. The envisioned short-range communication technology is Wi-Fi, while the long range is LoRa. We assume that short-range monitoring occurs in regions of interest provided with electricity, as the servers need a permanent power supply. Data from different regions of interest are integrated in the cloud, and the local server must be connected to the internet. The gateway can transmit data directly to the cloud if an internet connection is available, and the cloud also serves as a backup for the local servers. Our LoRa prototype is made by an eByte E32 module connected to an Arduino Uno board and to the rain gauge. The E32's frequency is 433 MHz, and the module does not allow to change several parameters, and the maximum supported payload is 56 bytes. We transmit 55 bytes of information, including a unique identifier that allows verifying which packets are received by the server. The received raw data is stored using the processing software for further processing that evaluates its performance. For the Wi-Fi prototype, we use one ESP32 board configured to act as a client, which is connected to the rain gauge, and another to act as an access point, which acts as a gateway. A personal computer connects to the access point, serving as a data server for the client, and we implement a TCP socket on the server, allowing the ESP32 client to connect to the server. Data is transmitted using JSON encapsulation, which increases the packet payload from 55 bytes to 350 bytes. The performance evaluation of both technologies is done by studying the communication range, the packet loss rate, the throughput, and the packet arrival delay, which I'm going to expose these parameters results for you on the next slides. We evaluate LoRa and Wi-Fi performances through real experiments in a residential urban environment, but with dense vegetation in the city of Petrópolis, that is in the mountain region of Rio de Janeiro, Brazil. The first experiment verifies the communication range of both technologies, and because the house is 4 meters higher than the street, the receiver is fixed 4 meters higher than the transmitter with no line of sight. The LoRa prototype reaches a distance of almost 200 meters in this environment, while the Wi-Fi prototype reaches 50 meters. After that, we fix the receiver at a location, and the transmitter position varies according to 3 scenarios. The blue spots are transmission locations, and the orange spot is the receiver location. The antennas of the transmitter and receiver prototypes of the LoRa prototype have a 3 dBi gain and are held on a vertical position perpendicular to the modules. In the first scenario, spots 5 and 6 have no line of sight with the receiver. The second scenario has line of sight communication with all transmission spots on the first floor. And the third scenario, there is no line of sight with the transmission spots. The measurements in each spot are performed 3 times for 10 minutes. The propagation environment is influenced by weather conditions and obstacles affecting the packet loss rate, which usually relates to the quality of the received signal. First of all, there is no packet loss for the Wi-Fi prototype due to the use of TCP socket, so the analysis is only for the LoRa prototype. Generally, more distant spots are more intensely attenuated and tend to present higher packet loss rates. This can be seen in the second scenario, which is an outdoor environment. In the first scenario, the highest average packet loss rate is found for spots 2, 3, and 6. Considering the antenna used is omnidirectional and spots 2 and 3 are close to the center of the antenna irradiation diagram, losses are more likely to occur. Spot 6 shows the highest packet loss rate because it is more distant and has no line of sight with the receiver. In the third scenario, the higher average packet loss rate occurs for spots 3 and 4, but a large confidence interval does not allow to make strong conclusions. The most significant losses occur for the indoor environment, scenario 3, but the packet loss rate is very low in all scenarios and does not hamper a rainfall monitoring application. The throughput is measured in packets per second. The Wi-Fi prototype reaches an average performance close to the LoRa prototype. However, the throughput of the Wi-Fi is more unstable than the one of the LoRa prototype due to the varying number of transmitted packets resulted from packet retransmission. This happens due to the reliable transmission strategies implemented by the TCP protocol and the media access control sublayer of the Wi-Fi technology. The higher the number of retransmission attempts, the smaller is the number of packets transmitted during the same time interval. Looking at the results of packet arrival delay, the delay of the Wi-Fi prototype is minimal and does not vary significantly. The LoRa prototype has a more significant variation and the median is higher. Besides that, the median remains approximately constant when we compare the results for the spots of each scenario. Compared to the Wi-Fi, the higher median for the LoRa prototype is due to the longer time on air of the signal sent by the LoRa module. After all of this, we integrate our prototypes to Dojo, an open-source Brazilian IoT platform. Dojo facilitates the deployment of IoT applications as it allows the visualization of collected data and the automation of actions based on predefined rules. We integrate our prototypes to the Dojo platform by sending MQTT messages with JSON payloads to unique identifiers of virtual devices configured in the platform. The virtual devices represent the real sensors, and the platform displays a chart for each attribute monitored by the virtual device. And now I'm going to show you a demonstration of this. This is a demonstration of how to use the Dojo platform. The first thing is to log in, and after that we have a few options of utilities. Considering our purpose to register data, first we need to set our own virtual device. For that, we need to perform the following steps. The video is a little bit slow due to the lack of memory of the computer where the platform is installed. The first step is to create a template where we include the several attributes that a physical device can collect. In our case, we have only one, the millimeters generated from the water pouring inside the rain gauge. The attribute needs a name, a type, which can be dynamic, static, or other, and a value, which can be a float, text, and others. After saving the template, we can move forward to the second step, in which we create the device. We need a name, and this is where we choose the template that has the attributes that we are going to monitor. After configuring the device, we save the configuration and a unique ID is created for the new device. In this page, we select the attribute that we want to monitor and the chart opens up for us. This is the ID created, which is used when programming the real device to indicate where to send the data. On the next video, I use another virtual device. This is its ID and the chart after receiving some data. The rain gauge with the LoRa or Wi-Fi sends a message update every time the rain gauge pours 0.25 millimeters of water. Now, the ESP32, which is the Wi-Fi module, is connected to the rain gauge through this black wire. I'm going to pour water to the rain gauge so you can see that the chart automatically updates itself. Before doing that, I restarted the Wi-Fi module. That's why the chart starts from 0. The same thing happens with the LoRa prototype. Thank you for your time. Now I am open for your suggestions and questions.
Thank you, Sophia, for your presentation. I'd like to open for questions. Who has some question for Sophia? Someone? So I will start to ask you a question. I would like to know about the rain gauge. What is its precision and how long does it take to communicate between the rain gauge and your system?
I did a test for 24 hours during the raining here. So I did this test only with the Wi-Fi prototype, and it worked really fine. It was really fast, the communication between the rain gauge and the Wi-Fi prototype. And I did a comparison between this test with the official rain gauge from here next to the house. And it was very similar, the results.
Thank you. Let's gonna see if somebody has any other question. No question? So let's thank Sophia for the presentation, and we start the last presentation of this session. Thank you, Sophia.
Okay, thank you.
The next presentation is entitled Cloud Strategies for Image Recognition from Bernardo Costa and Pedro Pisa. Let's start the presentation.
Have a good morning, and I would like to thank you for being here for this presentation on cloud strategy image recognition. And I'd like to give a special thank you for Diogo and Igor for making this event real. Thank you so much. Without you, this event wouldn't happen. In the demo session, I will talk to you about the cloud strategy for image recognition. It's a very important thing for creating new features on your application. Our agenda today is to talk about some image-based applications, understand the options we have in the public cloud providers, and see a difference between services and a platform in the AWS case study. So talking about image recognition, we have three major techniques that is most used: the image classification, object detection, and segmentation. Then talking about image classification, we have a group of images, the different groups of image that we want to classify an image into categories. The most common example of this technique is the cat and dogs classification. So we have an image and we need to classify it if it's a dog or a cat. Here we have another example of a plant pest classification that the model shows if the plant has a pest or not considered in the picture. And the second technique is the object detection. So instead of classifying the image in one group but multiple groups, we sometimes need to detect an object inside an image and also understand where the object is in the image. Then when we do the object detection, the model creates a bound box where each identified object classes are. So if we have an image with multiple cars, it will detect each car. And that in the example, if we have a plant pest detection, then it will show where in the image are the pests. That example, we have three bounding boxes with the pests. So that's an evolution of the simple image classification. And the third one is the object segmentation, where we classify each pixel of image so we can really understand where is the object of interest. So it's similar to take colored pencil and paint the objects in the picture. Then it's more there. It's not only a bound box, but a region on the image when we can understand each pixel composes the object finding. And when we look for the public cloud providers, the image recognition are presented in most of them. These all four cloud providers are the leaders one: the AWS, the Google Cloud, IBM, and Azure. For this demo, we choose the AWS that is the leader according to Gartner. Then we have two most common used services for artificial intelligence in the cloud. We have the AI services and the AI platforms. The AI services is used when it's not required so much AI theory understanding. So you do not need to have a machine learning specialist, a data science. It's not necessary for using to add features using artificial intelligence on your application. It's used for solve specific and common tasks, just like find a car in the image, understand there is a dog on the image, and something like that. It can be used for the developers because it's based on API calls, and the only thing you need to do to work with them is to call the API, the cloud API. And it sometimes do some simple things, so common things, not that simple, but just like test analysis, audio transcription, chatbot, image and video recognition is common example that are any cloud provider have. On AWS, the services for image recognition is Amazon Recognition. It's a service that makes facial detection, pathing, text detection, labels, and face search verification. And the only thing the developer needs to do to implement these on the application is to call an API to get the picture, call the API, and receive the return. It's very, very, very simple. We'll demonstrate in a minute. On the other side, we have the AI platform. It's designed to be the working environment for data science. Here, we need to have an understanding of artificial intelligence, machine learning, to understand how to explore the data, to train the model, to test, to adjust the parameters of the model, and then to deploy for use in the production. The platform helps the data science to implement all this. But if you want to customize your model, it's mandatory to use the platform, not the services, for a more customized model of artificial intelligence. In the Amazon platform is the Amazon SageMaker. It provides a notebook instance so you can explore the data, we can create the algorithms and implement and test it. It's very useful to have a Jupyter notebook there. Then we have jobs for training, track the training jobs, and understand, test lots of parameters, understand which is the best. Then we will have the models, so the better model, the model that works best. So we can save the model, host it, and then deploy and create an endpoint that will allow the developers to connect on the application. After we have the endpoint for our customized model, it's very easy for use this. It's easier for the AI service, but we need data science to get that to help this. So how to decide between using services and platform? We think that are three most important things to consider when choosing that. If you need to have the feature fast, you need agility to have it done, it's better for you to use the services. Because you just need to call an API, it's very easy to integrate, and you can use the services that better fits you. But if you want to customization, if you want to understand better, just like if you have an example, we can use Amazon Recognition to detect a car on image. But if you want to know the model of the car, then we need a customized model, so we need SageMaker. The more customization you need, the more you will need a platform for do that. And the last but very important thing to consider is if your users will need to use the model without an internet access. Because the AI services are a cloud API, so we need to have internet to call the API and receive the answer. But the platform, after you get the model, you run the model, you train it, you have a production model, you can get this model and deploy it in advice. It's very useful for IoT, Internet of Things scenarios, to have a model and then process there. There are cameras that can process image inside the camera and something like that. It's very important for automated cars, for autonomous cars, for working because it needs to process the models in the car, not depending on the internet access. So we believe that these are the three most important things to consider when deciding between Amazon a artificial intelligence services or platform. So let's go to our demo. I would like to introduce you Bernardo that will present us about the using of Amazon Recognition and SageMaker for detecting safety helmets in a construction environment. So Bernardo, it's you.
Amazon Recognition has a lot of features to analyze image, such as object and scene detection, facial analysis, or text in image. I will choose object and scene detection for this demo. Here is the demo image that Amazon Recognition gives us to show how easy it works. Here in the result section, we have all the classes that it found and its confidence. And if you click here, the request, you see this information, but in a JSON mode. That is how API works. So, for example, here, name car is a class, name is car, and the confidence, and in the instances list, you can see the bounding boxes that you can use to draw these boxes around the classes. To interact with Amazon recognition, you can click here, the request, to see how it expects our image. For example, you can create an S3 bucket, put your image in the bucket, and when you call the API, you pass the image path. In this demo, I will use the upload mode that enable me to upload an image from my computer. So I will click here. And open. Now Amazon recognition show me that it found two girls. The first one here marked as a person, the second one here person, and it found a helmet here. Note that Amazon recognition could not find the second helmet. So in order to use a custom solution with custom classes to resolve a custom problem, you can use the other approach that is Amazon SageMaker, which is the AI platform. The starting point in Amazon SageMaker is the notebook. Amazon SageMaker hosts a Jupyter Notebook environment for us to simplify the interaction with the cloud. Let's click here in Notebook Instance and here to create a notebook instance. Type the instance name. You can choose here the instance type and choose the IAM role that gives SageMaker permission to interact with other AWS services, such as Amazon S3. And then click here to create the notebook instance. I will cancel because I already created one. My instance status is in service. So I can click here to open the Jupyter Notebook or here to open the Jupyter Lab. I will choose the Jupyter Notebook for this demo. Now we will be redirected, and here is the Jupyter Notebook. It's the environment that data scientists will create custom models using Python or any data science framework they want. For example, TensorFlow or MXNet. Returning to Amazon SageMaker console, we can click here, Training Jobs, to see our training jobs. The training job is an Amazon SageMaker feature that enables us to detach the training from your notebook instance. So you can use dedicated GPU instance to train our models. So I click here to see these training job details, and you can see all configurations that I set and the instance type I use. So I use an MLP3 2x large, which is an instance that has GPU, and Here you can see the output. That is the model artifacts that we will use to deploy our model. You can deploy with Amazon SageMaker here in these sections of endpoints. With just a click, you can use this model to create an endpoint, or you can download the artifact to use wherever you want. For example, with a Raspberry Pi or other IoT device. So, in order to use the offline mode, I downloaded this model artifact to my local computer, and I use Python to load the model and make some predictions. So let's do it. This is the VS Code environment. So I have here the model, the params and the JSON, which are the files that contain our model. That's Amazon SageMaker create. And I have a folder here called raw that contain a lot of images. And the folder detections that contains the predicted images. So, and then in order to predict one, I will type here Python 3 detect underscore hardhat.py, which is my code that interact and creates the bounding boxes and the path of the image. So type enter to start. And the code starts and finish. So here is in the detection folder is the image that's contain the predicted. So here 0.jpg is raw image and 0 with in the detection folder contains the bounding boxes. For example, we can use the girl's image and to start a detection. Okay, it's done. And click here. You can see the bounding boxes around the girl's hard hat.
Thank you, Bernardo, for presenting us how to use the Amazon Recognition and the Amazon SageMaker. So, as Bernardo presented, the Amazon Recognition for Pro is very easy to do. We use the web interface of AWS, but we can call directly on any application, use the API. But the approach with SageMaker is very more customizable. We really detects both of the helmets here for the two girls with a very high confidence level, and also we implemented in the model the detection of the color of the head, because it's a very important information for construction. Each color is for a kind of professional. So using the customized models, we can detect multiple people, different positions, different helmet colors, and also a person without helmet, as we can see here on this image. It's very important for use in the construction environment for consider the safety of labor. Then here's another example, the different positions, angles, and something like that. It also detects the helmet. Then that was our demo. We present that it's very important to clearly understand the objective and the requirements of our application. Because if we needs agility, we do not have so much customization, and we do have internet access, it's really, really faster for using an artificial intelligence service, just like Amazon Recognition. But if we need a more customized model, we can use Amazon SageMaker or any artificial intelligence platform for testing our model. But it's very important for you to use pictures in different angles, rotation, and position so we can have a better model for the production environment. And also a good set of training data. It's very important to have multiple images, multiple types of images for you really test your model. So I would like to thank you for this presentation. Thank you for your attention and have a great event today.
Thank you, Bernardo, for the presentation. I would like to know if somebody has some question, please. Questions for Bernardo on YouTube or here on the chat. Marcelo Dias, he has a question. Please, Marcelo.
Yes, thank you, Diogo, and thank you, Bernardo, for the talk. It's an interesting approach. My question, I'm not sure you already answered during your presentation. My question is the following. Suppose, because you mentioned automotive applications, suppose you have several cars taking pictures of a crossing, whatever, something in the street. So you'd have like different sources of pictures of a given situation. For example, an accident. Would your approach be adapted to this kind of situation where all these cars would contribute with different angles, and the result should be given in real time, or would you propose something different for this kind of situation? Is that clear as the question, or I should make it again?
Thank you, Marcelo. If you want to predict from from car accidents in the street with IoT, you can probably use an approach like you show, that you use our model and extract from the cloud and compile to run in an IoT device. So it will be running locally. So you don't need the internet access, and you can communicate online with the device. When you say online, you are trying to say you can predict in real time.
Predict or identify something, for example, an accident, two cars that crashed, and you have other cars that are coming from different directions. So they could use they could collaborate to like classify and together send some specific information for the police or for the rescue teams, something like that. So my question would be like, would you need some sort of knowledge from other situations, like especially for the training part, or how would this work as a real-time reaction system?
You probably need a lot of information about all situations you want your model to predict, or your model to interact, or model to classify. But to run it in real time, you just need to export your model and apply it in an IoT device.
Right, I see.
Your data is more important to describe a lot of different situations that your model could be in.
Indeed. Okay.
Thank you, Marcelo, for your question. Thank you, Bernardo, for answering. I still have one question, but I don't know if somebody has another question here in the chat or on YouTube. Bernardo, I still have a question about the cost of this mechanism. How do you compound the costs of AI service and the AI platform? How do you compare them, and how do you compound this final cost for the user?
There are three points to compare the cost. The first one is in AI services, you pay for AI for API calls. So if your model has to predict a lot of image, your view will increase, but you don't have to worry about training. So you don't need to run GPU machines to train your model. So there are these two situations that you can handle in. So a lot of predictions, or you train your custom model and pay for the GPU instance.
Thank you for your answer. Any more question? No? So thank you, Bernard, for answering and for the presentation. And for now, we finished our second day of the event, and we hope that all the audience like it. And we're gonna be back tomorrow at 8:10 at the same channel on YouTube and also in WebEx. Thank you all. See you tomorrow. Bye.